So we need to differentiate the Taylor series centered at 0 for the given function. We also need to identify the function represented by the differentiated series, and we need to give the interval of convergence of the power series for the derivative. Taylor series of the function f of x centered at x equals a is given by f of x equals the sum from k equals 0 to infinity of k's order derivative of f of a over k factorial. So if we do the expansion, it becomes f of a plus f prime of a multiplied by x minus a plus the second order derivative of f of a over 2 factorial multiplied by x minus a squared. Wait, let me move this a little bit to the left. Plus third order derivative of f of a over 3 factorial times x minus a cubed, and so on. So Taylor series for the function f of x centered at 0 is given by, so we just substitute 0 for a, and we get that it equals sum of from k equals 0 to infinity of k's order derivative of f of 0 over k factorial, so it equals f of 0 plus f prime of 0 multiplied by x plus the second order derivative of f of 0 over 2 factorial multiplied by x squared plus the third order derivative of f of 0 over 3 factorial multiplied by x cubed, and so on. So in our case, f of x equals inverse tangent of x. Let's find the derivatives of this function. So the first order derivative of f of x equals 1 over 1 plus x squared. The second order derivative of f of x equals negative 1 over 1 plus x squared. And then f of 0 equals 1 f prime of 0 equals 1. The second order derivative of f of 0 equals negative 1. Well, that means that our Taylor series for the given function is given by f of x equals x minus x cubed over 3 plus x to the 5th power over 5 minus x to the 7th power over 7 plus x to the 9th power over 9, and so on. Now let's differentiate f of x with respect to x, and we get that f prime of x equals 1 minus x squared plus x to the 4th power minus x to the 6th power plus x to the 8th power, and so on. So it equals the sum of from n equals 0 to infinity of negative 1 to the nth power times x to the power of 2n, and it equals 1 over 1 plus x squared. So the derivative of f of x represents a series of the function f prime of x equals 1 plus x squared. Well, now when we know f prime of x, we see that nth term here, so an equals negative 1 to the power of n times x to the power of 2n. We will use the ratio test, so L equals the limit of the absolute value of negative 1 to the power of n plus 1 times x to the power of 2n plus 2 divided by negative 1 to the power of n times x to the power of 2n, where n approaches infinity. Then this equals the limit of the absolute value of negative 1 multiplied by x to the power of 2, and n approaches infinity. This equals the absolute value of negative x squared. So it just equals the absolute value of negative x squared. So we get that if we want our series to converge, this needs to be less than 1. Then negative x squared is less than 1 and greater than negative 1. So that means that x is goes from negative 1 to 1. So we say that the